Hello, my name is Carlos Zapata, and I'm here to talk about cognitive systems. If you know me already, you might know that I do research on mathematical physics and differential geometry. However, this talk has nothing to do with that. This is a little passion project of mine that aligns with recent developments in SEMF, the Spanish association that I chair at the moment. So I hope you enjoyed this talk. Alright then, let's begin with the talk. A Landscape of Cognitiveness. So this is the title I've chosen, and you note that indeed there is a word, they're strictly not in the dictionary perhaps, but I wanted to use it to convey an idea that I hope will be clear by the end of the talk. Now, before we start, let me give a motivation and a little disclaimer. So first of all, why did I get thinking into these topics? So my first motivation was to identify cognitive systems, in itself a concept cognitive system, quite hard to define in itself, that are something else than human brains or human nervous systems. So this was my initial idea and the thing that kept me thinking for actually many years. And then, well, I started doing a little bit of reading, and I put this little talk together as a motivation, mostly a self-motivation to further read into these topics, but also because I started seeing a unifying theme under the relatively modern field of cognitive sciences. And I think it's a field that is not sufficiently visible as a branch of science in itself, because indeed it agglomerates many different sciences. And this talk is a little bit of a love letter to the field of cognitive sciences. Now, the disclaimer, of course, is that I am not a cognitive scientist. I don't have any formal training on this subject, and this talk is mostly intended to evoke, entice, and illustrate. And so it should be taken as such. This obviously does not replace any further and proper training and proper reading on all these topics. So there will be links in the description, and all the green text on the slides are clickable if you do download the PDF that is attached to this talk. So I do invite you to explore the literature and do all the reading and all the training that is motivated by this talk. But indeed, this talk is just a big motivation and a sort of a grand statement of the importance of these topics and why I think they are exciting. Okay, so let's begin. So we always begin with human cognition as the center of our discussion. Indeed, because we are human and we have human minds and we are thinking in terms of human minds. So I just wanted to begin by listing some of the distinctive features that human minds appear to have. Right. So briefly, we clearly have goal-oriented decision-making. This is our daily life, and indeed we observe that in other animals, but it's indeed part of human cognition. We have symbolic communication. I am talking through words. You see the words on the screen. There's symbols everywhere, so we indeed have a very deep system of symbolic communication in place. Computing and logic, of course, you're probably watching this on some form of device that runs on binary logic, and we have mathematics, we have science that is strongly founded on all this higher cognitive concepts that have been built culturally and constructively for millennia. Indeed, something that is not observed in any other species and is quite characteristic of humans. Now, we have a very, very strong theory of mind. If anyone remembers a bit of anthropology and human history, you might remember that Homo sapiens was particularly successful in its social infrastructure, and that seems to be what made Homo sapiens so dominant in evolutionary terms. Now, of course, creativity in solutions, in finding solutions, it's also a very human trait that we seem to be able to think outside of the box, so to speak. And to think outside of the box, there needs to be an outside, and that's what we call cosmology. So human beings have a very good sense of cosmology, and this is a grand word to simply denote the notion of a whole, right? I mean, we do have a unified experience. We seem that something as distinct as having a glass of water in a warm day and doing maths in the afternoon or watching a movie in the evening, that all is part of the same life, of the same whole. That is having a good sense of cosmology, and it seems to be quite uniquely human, as we will see later on. And then finally, when many different human minds are put in place, some characteristic dynamics emerge, and ethical behavior and moral considerations appear, and then of course there are all these political structures that also prop up that we are all very familiar with. Okay, so now that we have the human cognition a little bit identified and sort of brought to awareness, let's try and go to the opposite end of the spectrum. Let's go to the other end of the sort of conceptual scale and try and abstract as much as possible what cognition could be, or what a cognitive thing is doing. in the real world. And this is, I want to illustrate this concept with the notion of the cognitive loop. Now, this is something I just summarized myself, and I do invite any expert watching this video to refer me to the proper literature and then proper terminology. But I think it is a good summary of phenomenologically what a cognitive system would probably end up being in general terms. So a system is something that is part of a world, and something that incidentally we can measure eventually. We are ourselves part of this world, or some kind of world. Now, I'm not specifying this is the real world or physical world or anything like that. It could be something, for example, programmed in a computer or whatever. But it's indeed some world where there are parts, and their parts, or the parts of the world, relate to each other in specific ways. And so that's how we're going to characterize systems within this world. So a cognitive system will be characterized in so much it relates to other parts of the world. So we're going to take another part of the world and we're going to call that an object. It could be another potential cognitive system, or it could be anything. And we're going to characterize the cognitive interaction between this our cognitive system, or the tentative cognitive system that we're trying to study, and we're going to see how it connects to other elements of the world. So the first line of interaction is what we call an input, or perception, perhaps. And this is an interaction between the object and the cognitive system, and it happens smoothly. It preserves the structural integrity of the cognitive system. It's something that is somehow fine, and it has a sort of usually a sort of a low energy transfer. This kind of properties that the scale of the cognitive system, the energy scales of the cognitive systems are much larger than the energy scales of the interaction that we conceptualize as input or as perception. Okay, so in particular, the structural integrity of the cognitive system is preserved throughout this input or perception process. And then what happens is that the cognitive system rearranges itself in a process that we call processing appropriately, and then in a fairly independent way, or fairly unrelated to the object, at least directly, and then it produces a form of outcome in behavior, and the cognitive system has a way to interact back with the object so that there is an action, so the object is transformed in some way. You can think of the most elementary examples, maybe a little child playing with a cube, and input is vision, and then action. Processing is the brain of the child processing the object, and then the action is extending the arm, playing with a cube and moving it. Now, the reason why I think this is so relevant and so illustrative is that this is a recursive activity. This not just happen once, but this can be looped, and it can be replicated over and over again, so that there is this constant feedback that can lead to the notion of learning and the notion of experimentation and so on. And so I think this particular scheme that is on the screen at the moment will be a template that fits well into the many examples that we're going to review. So the plan for the talk is see a few examples of potential cognitive systems that we'll see they all fit this cognitive loop, and they are quite fundamentally different in terms of their origins and structure, perhaps. And then in the end, we'll see really how structurally different they are, and then comment on some of the conclusions that we can derive from this, and in particular argue for the concept of cognitiveness. It's a made-up word that we need to justify by the end of this talk. Okay, so let's get into the first category of examples of cognitive systems, which are non-human nervous systems. So we're going to look at two big classes of non-human animals. So the first are apes, because they are nervous systems that are very close anatomically and genetically to our system. So we can think of them as a bit of a infinitesimal deformation of our own cognition in some sense. And then we're going to look at cephalopods, which are essentially the most distant cognitive animal that we find in the world right now. So we're gonna just give a few hints and a few references on this, just to paint the picture of cognition in the animal kingdom. Okay, so let's review briefly ape cognition and social dynamics. So what do we see in chimps mostly? Well, great apes, orangutans, gorillas, etc. So the first thing we see is communication. So communication does happen, symbolic communication that is, does happen naturally in chimps, in great apes and non-human great apes. Indeed, to a sophistication that is much, much lower than in humans. In fact, the famous examples of chimpanzees using sign language has been somehow debated for many decades, because it's not clear whether there is an actual understanding of the language that they are using. It's more of a collection of signs, and it's an impressive collection. At times it's hundreds of different signs and ways of combining them, but that doesn't seem to be an actual deep understanding of the functioning of that language. So it falls under perhaps falls under the imitation and pantomime sort of behavior that is indeed common in many other species. Now, the other aspect of chimpanzee cognition that is very striking for a human that witnesses it is the theory of mind. Chimpanzees and great apes in general have a very good theory of mind, and there are many studies that show how chimps know whether a chimp knows, and this is something that is highly non-trivial, and that's what ethologists call a theory of mind. This sounds as a grand concept, but it's essentially having a notion, a cognitive notion of the mind of others, right? So that is something that has been checked time and again in research, and is something that's probably quite similar to us in that respect. Now, what is also very similar to human societies is the presence of morality and politics. Indeed, phenomenon like altruism, phenomenon like tyranny and democratic rights, and in a very primitive way, are observed in natural clans, in wild clans of chimpanzees. And I do invite you to explore all these links, which are down in the description and in the attached PDF. So all the green texts are links to the literature where you can delve, and they're actually very easy reads. They're some of them are quite technical, but they get to the point fairly straightforwardly. So I invite you to read on all these topics. Now, moving on from apes and our closest relatives in the animal kingdom to the most alien relatives that we could have, I would say, in the animal kingdom, and this is cephalopods. So cephalopods are an absolutely amazing kind of animals, because they are a good example of the saying mind over body. And so how can we summarize the evolutionary interest of cephalopods is indeed the fact that you can have some ammonite in the Cambrian period, hundreds of millions of years ago, with a very hardened shell, very defensive evolutionary strategy. Clearly, it's not the fastest moving animal, so it will be vulnerable to predation, and so that hard shell will be indeed a very, very good asset to have. Now, fast forward to the present, and we find these absolutely adorable animals, the cuttlefish. So how did this happen? How did these animals essentially lose the shell when apparently there's nothing to be gained? It's essentially the same animal, just without the shell. So what was selected here was intelligence, and these animals are highly intelligent, especially for being invertebrates. Again, vertebrate is not just a terminological classification. It is anatomically a big difference in terms of how the system is organized. And so the fact that these animals are highly intelligent and highly cognitive, at least as far as we can tell for now, there's a lot of research to be done, but so far we can tell they're highly cognitive, is quite striking. And so the evolution of intelligence in cephalopods is many times used as a benchmark for how, for example, human intelligence was also selected by environmental pressures and relations and social relations between the different individuals. So indeed a very, very fascinating topic. So very different animals from vertebrates, even not just apes, but vertebrates. And I also recommend reading Other Minds, a book about some colonies of octopus that show behaviors that are indeed well beyond many behaviors of many vertebrates, even not just for invertebrates. So indeed a very interesting class of biological potential cognitive systems. Okay, on to the next category, artificial neural networks. This is a hot topic right now. I'm sure many of you watching are very aware of the recent advancements of artificial intelligence and how prevalent it already is in our technological environment. So I want to stress two recent developments, both spearheaded by DeepMind, the AI company from London that mostly deals with the interaction with humans, because it's where we're going to be benchmarking our A's against, at least in this brief summary. So the first thing I want to comment on is AI agents in competition and cooperation with humans, and then briefly mention some results on the dissection of AI brains. Now, this is a very interesting concept because, of course, the bane of the neuroscientist is that the moment you dissect a biological brain, well, the brain ceases function and the animal dies. So there's no longer the sort of functioning research that can be done. However, in an AI, this is obviously not the case, and you can dissect and you can see the brain, or quote unquote the artificial brain, operating in real time without any trouble. So I'll make some comments about this. So I will just focus briefly on one single example of a recent triumph of DeepMind's artificial intelligence, and this is the AlphaStar algorithm, or the AlphaStar sort of cohort of algorithms, which attempted to beat human players in the video game StarCraft 2. Now, for context, for those of you who are unaware, StarCraft is a video game that was released in 1995, if I remember correctly, and has had an AI community around it since its inception, pretty much. And it's been an open problem, to put it in these more mathematical terms, to tackle and to actually produce a general AI that could beat humans consistently, not even at the highest levels of competitions, but just consistently for average level players. And this is not really possible. And everyone who's familiar with the game knows that the moment you learn the few basics, the first few months you play the game, the AI that comes with the game is insufficient to pose a challenge. So this was an open problem, and traditional programming seemed insufficient. So the big success of AlphaStar was indeed beating human players, and indeed beating the pros, as we will see in a second. So let me just play this little animation to give you a hint of what's going on. So this is a summary of AlphaStar playing against Mana, a Polish professional player, and you can see a little bit in real time how the AI is operating. So the AI is taking the input directly from the screen as the player, as a human player, and you can see a little bit the real-time reaction. So you can see the position in the minimap where the AI is aiming, or you can see all the options, all the little dots. So in the bottom right is the different units you can create in StarCraft. StarCraft is a real-time strategy game. You build your military buildings and military units, and you move them around the map. You give them commands, and they fight the enemy units. So it's indeed a very visual way to summarize that this was an AI agent that was essentially doing the same as a human. And then you can look at in the middle right, you can see this diagram that says outcome prediction, and you can see that the AI is doing fairly well. The outcome prediction of the win percentage seems fairly high. So our poor player Mana is not doing that well against the artificial intelligence here. Okay, so why is this relevant? Why am I taking this particular example of StarCraft and not perhaps chess or Go or other games or other competitions between AIs and humans? So the reason why I selected this particular example is that, well, StarCraft 2 is a game that was selected by DeepMind precisely because of its similarity with the real world. And let me explain this a little bit in a bit more detail, and let me illustrate why this is a huge deal. The fact that there was an AI that was beating consistently, and by as of today, it's consistently the best player in the world as it stands. So the first obvious thing is that this is a real-time game. So most of the tasks that had pitched AIs against humans before were discrete in nature, and they were played by turns. They're taking turns, right? So this is perhaps not a very significant change, but it's indeed an important one, at least to have a sense of interaction between AIs and humans, right? Because you can always think, well, there's so many computations that a computer can do faster than a human, that the fact that you can take arbitrary amount of time between moves, it's a little bit strange. But the fact that this is real time is puts some constraints that makes the interaction between humans and AIs a lot more natural, right? Now, the very important thing about StarCraft is that the game space, the possible set of states and configurations of moving pieces, so to speak, is huge. It's ridiculously high. It's essentially virtually infinite. There's so many states that no computer that was attached to the program when the simulations were running, when the AIs were running, could actually comprehend that amount of data. So you needed an intelligence that reduced the complexity of all those possible states and actually somehow, in very broad terms, understood what was going on to reduce the complexity. Because something as simple as taking your initial worker to place the initial building, you have thousands and thousands and thousands of possible positions for that initial worker in that initial building, and that's just a fraction of the possible decisions you make in the game. So the game space is absolutely enormous, and so you need a cognitive algorithm to deal with that complexity, because what's important about this is, well, there is imperfect information, and then there's also constraints for the AI that are exactly symmetrical as for the human players. So that means that the AI could interact with the game, so this is where imperfect information also comes in. The AI could only interact with the game exactly in the same way that human can. So the AI did not know anything about the coding of the game, did not know anything about the actual running of the game. So they only had access to the screen as a human player does, and they could only input actions 150 counts per minute. So 150 actions per minute might sound high, but professional players have about 300 or 400 actions per minute. So it was constrained to be an average player, and it could only perceive the game exactly the same way that a human does. So they would never know exactly what things were. They would just see pixels on a screen. And so it was that direct and that faithful of analogy of a learning process. And so anyway, so I'm not an expert on AI again, but for those interested, here's the links, and indeed these systems use neural networks. So these are artificial algorithms. So these are programmed on computers, the traditional binary-based computers, but they emulate the sort of the architecture of biological nervous systems, as we will see a little bit in the end. And these are called neural networks for that reason. And then they used a lot of imitation learning from taking sort of samples of games that were already successful games, or training data, as it's sometimes called. And then they had reinforcement learning. So every time they won games or they achieved certain objectives within the game, they would be given some internal reinforcements, which again simulates the way biological neural systems operate. Okay, so briefly before we move on from this category, let's talk about a different game, a different cooperative versus or / competitive scenario for AIs and humans, and this is capture the flag. So in capture the flag, you had agents in space that they could navigate, and the aim was to go to the opponent base, take the flag, and retrieve it to yours, and then score. And so what was really interesting about this project is that AIs and humans were pitched in 2 versus 2 matches, and any combination was allowed. So it could be 2 humans against 2 AIs, an AI and a human against 2 AIs, etc. Any combination was allowed. And the really interesting thing is that AIs were trained in similar ways as for StarCraft 2 or chess or all these other neural network recent achievements. And what was really interesting is there was given no particular reinforcement for strategies that were understood by human players, as good as home-based defense, opponent-based camping, or a teammate following. These strategies that have been agreed in the community, in the FPS community, where capture the flag is a mode that is typical. All these ways of playing had not been hard-coded, had not been given to these AIs, and had not been even motivated. So they were discovered, and they were selected somehow as the most successful strategies, and they were observed as this little animation showcase. So these are AIs playing the game, behaving with these very characteristic strategies that anyone who gets introduced to this capture the flag mode in FPS games needs to learn about. So what is important about this particular study, which was also done primarily by DeepMind? So there's a few things that can be extracted from this, and perhaps the most important one has to do with this notion of dissecting the brain and looking at the brain of the AI when it's operating. And again, there will be a link at the end and you can look at the details, but the researchers confirmed that the game world was indeed represented in the network somehow. So there was a topological representation of the interconnected rooms, etc. So there was a little bit of mapping between the physical or geometric environment of the AI and its neural network. So there was a little bit of topological equivalence between the two. But most importantly is that they could detect what could be referred to as bit neurons, where the most successful agents that were, after competition against each other, were selected as the most proficient in playing capture the flag, had either single nodes or set of nodes that acted as essential bits of information. So for example, they could encode the enemy has the flag or the enemy doesn't have the flag, and that Boolean value of true or false, does the enemy has the flag, is true or false, that Boolean variable was encoded indeed in the network in a completely emergent way. It was never hard-coded to be there. It was just sort of found as an adaptive process. The programmers never put this structure there in the first place. So that's a very evocative result to the appearance of logic and perhaps a more binary thinking and rational thinking from merely adaptive behavior. Right? It's a very interesting. It's a very interesting case of that. Now, of course, the cooperative behaviors were naturally discovered, and this is without any explicit reinforcement. They were not reinforced to be cooperative. They just discovered cooperation as the most efficient strategy. And then, perhaps more anecdotally for our talk, is that human agents typically deemed AIs more cooperative than humans. So this was a situation where humans reported after playing that their fellow teammates were likely to be human because they were very cooperative, when in fact they were AIs. So it's a bit of a point of reference for how far things have gone in this field. Anyway, so here's the link for any extra information anyone might want to check out. Okay, so the final category of cognitive systems that I want to review is a little bit unorthodox, I would say, to consider at first. But hopefully by the end of my short presentation, you would agree with me that this is indeed a very, very interesting possible case of cognitive system, or at least it should be. And it's of course ant colonies. So I want to emphasize two aspects of ant colonies. First is organization. Ant colonies are perhaps the most amazing self-organizing systems that we know in the planet today. As we will see in a second, it's a case of no design or no apparent hidden design and an extreme organization. And then, and most importantly, to the point of our current topic, is the hive mind hypothesis, or what in the past have been an allegory of the hive behaving as a superorganism, and using this analogy to understand the interesting and perhaps shocking behavior that we observe of colonies, to think that there is a mind behind that process. That in the past that was merely used as an analogy, but we will see that actually recent research shows that this might be more than an analogy. Okay, so let's have a look. So if anyone is unfamiliar with how ant colonies operate, well, I invite you to do a quick search and go to the standard literature or watch some documentaries. It's absolutely incredible. But the most important thing about for our topic of discussion here is the fact that there is no design in the colony. So what does it mean? So let's consider another arthropod that also displays somehow striking design in the wild, which is a spider's net, right? So, for example, so spider's net is somehow encoded in the spider's DNA because the spider has all the instructions to somehow produce it. So that information of that structure is somehow encoded in that single organism. Now, a single ant does not have the information to the structure of the colony, not at all. And we know that, as we will see in a second, for reasons that have very, very striking similarities with human psychology, but also just if we look at the structure of a colony. So in a colony, we have a queen laying eggs, we have egg hatcheries, we have the trash room, we have organization, we have storage, we have, when there's surplus of food, there's storage, we have a nursery system, and larvae are handled in different ways depending on how the environment is behaving around the colony, and there is all this extremely complex behavior that has no orchestrator. There's no single organism, there's no single biological animal that is orchestrating all that complexity. So one is led to believe that there is something about the interconnectivity of all these elements in interaction that creates all this order. And one can always be skeptical, and I'm not at all an expert on this topic, so I don't want to go too much into sort of the deriving conclusions myself, but I want to present the evidence that we have today. So the Hive Mind hypothesis rests primarily on a few observations that have been made for the last few decades, or have been known for actually as long as we've known ant colonies, but have recently been given the status of what can be studied under cognitive sciences. And I will basically essentially review the literature and quote the experts. So, but the first observation before we do that is that indeed ant colonies fit the cognitive loop that we presented at the beginning. So both biological nervous systems and AIs were, both because we are biological nervous systems and because AIs are made to compete with humans, they clearly fit in the cognitive loop because they are either evolved to do that and we are that, or they are designed to do that. But now ant colonies are not obvious to fit this cognitive loop, right? So how do ant colonies fit the cognitive loop? Well, they fit the cognitive loop by having the process of interacting with the environment. So, for example, if you have the experience of dropping some food near an ant colony, you probably remember that at first you see one or two ants sort of strolling a bit randomly around the food, and then if one of them comes into contact with the food, then maybe goes back in a direction, and then a bit later another comes, etc., etc. And so there is a process of releasing chemicals and communicating both spatially and chemically between the ants, to the point where you see an entire path of ants that go to the food and chew on it or try to move it towards the center of the colony, and then effectively by the end of the process there is no food where it was dropped in the first place. So that could be analogous to a human being being hungry, then spotting some food, then reaching out with the arm and taking the food to their mouths and then swallowing it. It's a very similar process. In fact, the digestion and the whole process that goes afterwards is also analogous to what happens in the colony. So that's what we mean by the ant colonies fitting the cognitive loop. That there is a sense of sort of taking an input and processing and then generating an output. Okay. Now, another very interesting fact that somehow supports this interpretation of ant colonies is the fact that there have been studies that show that colonies have some form of memory or some form of personality, perhaps, that depends on their history, and to the point that you need this information to make predictions on how ant colonies will behave in the immediate future. So under control conditions, it has been observed that similar conditions produce statistically significant different outcomes based on previous history of ant colonies, and therefore given the idea that there is a sense of memory in the colony. And what's relevant here is that these memories are kept for way longer than the lifespan of any individual ant. Therefore, it's impossible that those memories are kept in the nervous system of an individual ant, because that's always a possible critique. You could think, well, I mean, ants do have a nervous system, I mean, it's a very rudimentary nervous system compared to something like an octopus or like an ape or a human, but they are sophisticated nervous systems. So there is the possibility that those memories are stored in some of those individual ants. But the fact that these memories last way longer than any singular lifespan then leads to the conclusion that indeed there is something memory-like going on. And then lastly, I simply wanted to mention or actually literally quote recent research on ant colonies where psychological techniques, that is human psychological techniques, or at least developed for humans in their origins, have been applied to the study of colonies. And so this is, I think, what summarizes perfectly the point I want to make about ant colonies. And I invite you to follow the links that are at the bottom. And I will just simply read one of the quotes from one of the lead scientists in this field. So Stephen Pratt says, "A brain or a colony processes information about its environment and about its own state, and then produces some adaptive behavior that's appropriate for the conditions." He says, "You can call that cognitive." Indeed, research shows how the superorganism concept is more than an illustrative analogy. So this is Stephen Pratt talking about colonies, and you can check the Psychology of Superorganisms, the publication. The Mind of the Anthill is more of a public science article, and it's very, very approachable. And I do invite you to explore this topic. It's really fascinating. Okay, so we've talked about three large categories of systems that seem to have something in common, and that we could deem cognitive just by analogy, just by the fact that, well, they kind of behave in this way. Well, AIs are kind of made to behave in this way. And we can indeed do that and just, leave it at that and have a nice discussion afterwards and be inspired by all this diversity of examples. But actually, I wanted to go the extra mile and use some of the recent or relatively recent theoretical developments in what's called network theory to actually discuss a little bit the structural similarities of all these systems, because they do have something structural in common, and I think it's already apparent from our discussion. But I want to discuss it. I want to go into the details a little bit more. So the first thing I would do is talk about network theory very succinctly, very briefly, because it indeed provides a powerful formalism to abstract fundamental properties of all these systems, and then in turn that would allow us to give quantitative comparisons and make more definite and systematic comparisons between these systems, and therefore lead to a more systematic science of these things. So briefly, what are the basic features of a network in the sense of network theory? So for the mathematicians in the audience, these are essentially directed graphs. But for the rest of mortals, we understand a network simply as a set of nodes that we abstract as something having almost no internal structure, and then links, which are essentially paths or connections between these nodes. You might want to have different kinds of nodes or different kinds of links, or have a little bit of structure inside the nodes to represent systems that are a bit more complex. But essentially, that's the idea. Okay. Now, how do we parameterize a network? What are the main features of a network? The main metrics of a network? Well, there's an obvious size, so number of nodes, the aggregate number of nodes. These are all the nodes in your network. There is how connected it is, right? So we could, for example, measure the average number of links connected to a single node. So some average measure of how connected it is. I mean, there's many ways of characterizing connectedness, but this is a simple, intuitive one that will be useful for the illustration that I want to do in this talk. And then finally, networks will always abstract something that is quite complex usually. So you might want to throw in a little bit more granularity and a little bit more complexity and a little bit more detail, usually in the form of different kinds of links or nodes having different states. So you will see in the examples that it's quite obvious that nodes need to have states, and in the more computer sciencey context, you might think of nodes, for example, keeping some set of variables and having values for those variables inside them somehow, right? So you might want to to characterize that as, you know, the number of data types that a node keeps, or the number of possible states that a node can be in, right? So it's just some rough notions. We're not going to get into any mathematical details, of course. It's just for the sake of illustration. Okay, so these basic features allow us to very, very roughly give an overall picture of all the systems that we've discussed so far in the talk. So let's have a look. So how do we read this table? So we have human brains at the top, and we can see that here we have the different systems, and we're going to list what is the nodes and where are the links. So what is the network that makes the system, and then we're going to give some estimates of the metrics of that system. So for example, for human brains as reference, we're going to have our nodes being the neurons, the individual neurons. The links, of course, are the synaptic connections between the neurons, or the direct influence between neurons. Then we count the number of neurons. We know that we are in that rough order of 10 to the 11 neurons. And then we look at the literature and we check that the average number of neurons that a singular neuron is connected to is roughly around 1,000 on average. So we write a 10 to the 3 order of magnitude in connectedness. And then in terms of the node complexity, S, remember, is measures the node complexity. We're basically just going to illustrate 3 kinds of nodes. We're going to have biological neurons, neural network, artificial neural network neurons or nodes, and then ants in an ant colony. So in those 3 cases, the biological neuron has a moderate complexity, because it is fairly more complex than a computing node in an AI algorithm, but it's way less complex than a full ant that is itself made of hundreds of thousands of neurons and has all kinds of metabolism and physiology going on in the system. Okay, so that's how we read this table. So we have the human brain at the top. This is always the notion, right? That we're looking down to other fellow cognitive systems in the world. But perhaps you want to change this point of view by the end of this talk. This is a little bit the whole point of this. And then you can see how it compares to a chimpanzee brain, for example, an octopus brain. You can see that there's just a game of numbers here. I mean, in terms of raw numbers, you can already spot differences that are apparent. And perhaps these numbers are, again, very rough estimates, and themselves are just an illustration. They're here just to illustrate. But I just wanted to make the case of the orders of magnitudes themselves. If you identify elements that will be somehow interconnected, you can see that indeed something like AlphaStar that has 10 to the 7 different variables or different parameters that will be readjusted. Again, it's not really fair to compare directly that number to the number of neurons, perhaps, but indeed it's something similar in some sense, and at least the number, the order of magnitude is certainly getting there. And so it's perhaps no joke to think that these things are actually realistically getting somehow physically close, or in terms of pure numbers close. But the most important bit of information I wanted to highlight from this table is indeed the ant colony. So the kind of network that an ant colony forms as a possible cognitive system is considerably more sophisticated than a brain in particular, right? So indeed, the total number of nodes is quite lower than, for example, a human brain. It's typically around 500,000 of individuals in the big complex colonies that are known in the world. However, if you think about how ants operate, in principle, all ants can be connected to all ants. I mean, obviously, timescales will be very, very different. But if we sort of account for the timescale difference, there is in principle a connectivity that is much, much higher, to the point that, because ants move and they can traverse different parts of the colony and so on, in principle every single ant can be in contact with every single other ant, and that creates a degree of connectivity that is way, way, way higher, than is several orders of magnitude higher than in any other of the examples of cognitive systems that we have here. And in particular, the type of connection and the complexity of the connection between the nodes, if we think of the ants as the nodes, is considerably more sophisticated than for example, the synaptic link between neurons, and let alone the convolution connections in an artificial network, right? So I just wanted to highlight that as in terms of numbers, and also have a summary of the rough orders of magnitudes of all the systems. Also to make the general point that we have at our disposal a theoretical framework where all these systems can be studied on equal footing. And it's of course in early stages, and there's a lot more work to be done, but it's a very promising prospect of having hard science of cognitive systems. So indeed, cognitive science having a more systematic and more empirical method to run with, right? Okay, so as a closing of my talk, that I think that's quite a lot of information already, I wanted to again go back to the original concept that I opted to begin my talk with, which was this funny word cognitiveness. That is not cognition. Is the property of being cognitive somehow. And I just wanted to basically make a point to say this is an important topic. Let's think about it. Let's study it. Let's enthusiastically research on this matters, because I think it has a very promising future. And so what I want to say about cognitiveness is on the first hand, is it a physical property of a system? Is it something that we can measure? In principle, it should be, because indeed it is part of the real world. There's nothing mysterious about a community of ants that is operating. I mean, there is a very complex system, of course. There's the barrier of complexity, but in principle, one should expect that given sufficient theoretical framework and fine enough empirical methods, we could, in principle, have a systematic science for these kind of phenomena. And clearly, there is something distinct and characteristic about certain kinds of systems in the world and not others. I mean, clearly, the droplets of water in the sea, I mean, could have a degree of complexity, perhaps in some sense similar to a colony of ants or a human brain, but we don't observe behavior that is comparable to a human brain or a colony of ants. So this is something that is something that I really think that should be explored, and possibly all these concepts will aid in that future research. And then secondly, and perhaps the message of the talk, or the takeaway of the talk, is a little a hint to my mathematicians. A little joke is the continuum hypothesis of cognition, right? So can we perhaps calling psychocentrism, our tradition of thinking of human cognition, of human mind, as being somehow the privileged way of cognition, could we do away with that and have a more generalistic approach to cognition, and just have a landscape in which we might be closer to chimps in some way, but closer to artificial AIs in another way, but we are none is better or more than other in some sense. It's just a landscape of different possibilities and different modes of cognition or types of minds. And just with this concept, I leave you with a few examples, a few speculative examples of what could be other minds. And this is indeed just speculation. It's just my imagination running wild, and some enticing ideas to think about as the closing of the talk. So, for example, we could have what happens when we have several brains, or no brain, or no clear center of computation. We could have a decentralized processing, a type of cognition that we could call decentralized. If that system is to become conscious in some sense, not getting into the problem of defining consciousness, but if that system develops something like our consciousness, it would probably sound like something like a committee of consciousness. And this is something that is mentioned in the book Other Minds, about the octopuses. And so one potential example is indeed the octopus, because apparently the anatomy of the nervous system of octopuses is so that there are so many neurons in the tentacles that it's almost like a committee, where the central brain is acting as a moderator of the 8 brains, one per tentacle. So that's one possibility. The other possibility is that, and perhaps the one that I find most exciting, because it's really quite different from what we are used to, is a little reflection on how we perceive our sensory input, right? So sensory input is usually perceived in channels that are very, very thin, and their bandwidth is way, way shorter than the actual size of the processing unit, right? If you think of the nervous complexity, the anatomical complexity of an eye or a tactile sensors and stuff like that, compared to the complexity of the whole brain, you can see that several orders of magnitudes of indifference in complexity, right? So there is in most of the cognitive systems that we study and we design artificially, there is this very stark separation between the sensor and the processor, right? There is that separation, and usually the sensor is quite simple and the processor is quite sophisticated. So what happens when the sensor and processor are one and the same, and the whole system is both a sensor and a processor simultaneously? So if such system were to develop some form of consciousness, what would that be? Is it dispersed? Because we clearly associate our consciousness with being somewhere, being a self somewhere somehow. So maybe it's a dispersed kind of consciousness. That's a little bit speculation. But this case is particularly motivated by the example of an ant colony. Because in an ant colony, even though there is a little bit of specialization in different ants that play different roles, essentially speaking, the entire colony is at the same time somehow processing and at the same time constantly sensing everywhere. Every single ant can be a sensor in some sense, and at the same time it's also a computing unit. So that little speculation is inspired by the ant colony, right? And then finally, if we agree that cognitive systems have some essential network structure that they manifest, then it's very natural to propose, especially as a mathematician would do, is to say, well, if this is the required structure for a cognition, now replace whatever you had in your nodes by a full cognitive system and make that into a new cognitive system. So this is a network of cognitive systems that in itself would be considered a cognitive system just structurally, right? And so perhaps, for lack of a better term, this could display a form of hyperconsciousness in some sense, in the sense that there is a consciousness going on in a system where each of the atomic parts of computing power also have consciousness in some sense. These two consciousnesses probably will never know of each other and be able to interact in any meaningful way. And so, of course, the example is not mine. This has been discussed many times by many scientists before. But a very possible and clear example of this could be indeed the internet. If one makes the case of how perception works and what the world is for internet, and how the sensory input arrives in the internet and how the processing goes and so on, one could think of human beings being the processing units, and then the entire network having some form of mind of its own, and so this is the classic, is the internet aware of itself, and so on. So I leave you on that note, and more of a fantastical and a speculative note to think about. Hope you enjoyed. See you next time.